Lesson 14, Non-Standard Maximization Linear Programming Problems. Objective 1, Standard and Non-Standard Linear Programming Problems. For a non-standard linear programming problem, it is defined to be a linear programming problem that cannot be written as a standard maximization problem. Let's recall what a standard maximization problem is. A standard max problem has the objective function to be maximized. Each constraint is written with a less than or equal to inequality. The number after the less than or equal to inequality is non-negative, which means it's 0 or positive. And we have the non-negative constraints for each variable. So for our examples, first we want to identify if the problem given is a standard max linear programming problem, and B, state the solving method neither, either standard or non-standard simplex. And it goes along with the name. If we have a standard max problem, we use the standard simplex. If we have a non-standard problem, then we use the non-standard simplex. So for number 1, we have the maximize in our objective function. If we look in the center, we have less than or equal to, and the numbers after the less than or equal to are non-negative, 0 and 10. And then we have our non-negative constraints for each variable at the bottom. So this is a standard max, which means that we're going to use the standard simplex on it if we were to solve it. That uses the method we used in lesson 13. Second problem. Again, we have our maximize at the top. Now look at our constraints in the middle. We have a greater than or equal to and a less than or equal to. These are not both currently less than or equal to. However, we can change that. If we take this first inequality and multiply both sides by a -1, then that will flip the inequality. So we have now our maximize stays the same. Maximize p equals 2x plus 3y. Our subject to, when we multiply by the negative, we now have x plus 2y is less than or equal to 12. There's our less than or equal to sign. Our second constraint was 2x plus y less than or equal to 12, also a less than or equal to constraint. And when I look at both the numbers after, they're also non-negative. So this meets the second and third criteria. The last criteria is all of the variables must be non-negative. X and y were greater than or equal to 0, so that meets our fourth criteria. That means this is a standard max when we rewrite it. So we will use the standard simplex method. On to number 3. Maximize p equal 20x plus 50y. There's our maximize objective function. 3x plus 4y less than or equal to 72 has a less than or equal to sign. 5x minus 2y is greater than or equal to 16. So again, we see the wrong inequality. So our trick to make it a less than or equal to was to multiply by a -1 on both sides of the inequality. Maximize p equal to 20x plus 50y, subject to our constraints 3x plus 4y less than or equal to 72 stayed the same. Our second constraint multiplied by a negative, so now we have -5x plus 2y less than or equal to -16. Now we have our less than or equal to. However, our number after the second constraint less than or equal to is a -16. That means we do not meet the condition that we need a non-negative after the less than or equal to inequality. So this was our third criteria. Was not met. We still met the fourth one again, x greater than or equal to 0 and y greater than or equal to 0. The only one not met here was the third one where we had to have non-negative numbers after the less than or equal to sign. That means this is a non-standard linearization problem, and we're going to use the non-standard simplex method, which we will do after we finish this first set of examples. Number 4. This has our maximize again at the top. We have a less than or equal to, but in the second one we have an equal to equality. This is not going to be made into all less than or equal to non-negative numbers when you see an equal. We can still do these problems with the equality, but we'll get to that in our third objective. So because of this equal sign right here, this is a non-standard linearization programming problem, and we're going to use the non-standard simplex method. We will work on solving example 3 in our next objective when you can continue on to objective 2's notes, and example 4 will be solved when we continue on to the third objective.